Okay, I'm gonna get started. So, welcome to the second review session of ENGR 210. Uh, this past week, you have learned hypothetically about the node voltage method and how to solve circuits using that. And I believe that is what your quiz will be mainly on. That is what your homework was entirely on. That's my name. I don't know why I was writing that. I was trying to write the date. Today is 1/30/25. Uh, but yeah, so we're gonna do some, I'll do some review of what mesh or what node voltage is, and then some example practice problems. And yeah. Oh, actually, first I've decided that I'm going to start by just briefly going over the previous quiz and how you were supposed to do it, or what the correct answers were, because these are actually all posted on Canvas. Like after a quiz, Zorman posts the answer key to the quiz. So if you want to check that yourself, you always can. But here, I'll go over it real briefly. So for this first question, it said use Kirchhoff's laws to find the power associated with the independent voltage source. So you are trying to find the power associated with this thing. So that means to find the power through it, we have to both find the voltage across it and the current going through it. We don't actually know which way the current's going. So one thing that a lot of you messed up on this quiz, I noticed, is that I'm getting shut up. Okay, sorry, I got a phone call. I think it was a spam call. Um, but a lot of you treated this as a voltage source. See that arrow? This is a current source. There is like we know nothing about the actually no. Okay, so this is a current source. So it is creating some current going up. We actually already know the voltage across this current source because here we see that this thing has 15 volts across it. It's given, right? There's 15 volts between this point and this point. And since these are connected by wires, there's also 15 volts between this point and this point. So that's just some information that a lot of you missed. A lot of people were like trying to do KCL or Kirchhoff, yeah, or this is KVL loops, and then they'd write like 5 ohms times I something plus zero point 0.5 IX. You cannot do this because this is a current. And for the thing where you do the loop, you're talking about the voltages of the components. So keep that in mind when you are doing problems. But anyway, back to how Zorman recommends doing this. So to start, you can very straightforward find the current going through here because you have both the voltage across this resistor and its value, V equals IR. Right here, you find that this is 3 amps. Then we look at this node and we say, okay, we have a current going in, a current going in, and a current going out. This is IX. This is 0.5 IX. So that means we have 1.5 IX in total going into the node. And then we have some current I5, which we have actually already found is 3 amps going out of the node. So we can write this to say that the stuff going in is equal to the stuff going out. You can write like 1.5 IX equals 3 amps, or 1.5 IX minus 3 amps equals 0. Most people got this. So then you end up finding that IX equals 2 amps. Then, last but not least, we have to do kind of this last section where we look at this side, because we found the voltage here and here, we found the current here. Now we just need to find, so okay, another thing, since we found IX as 2 amps, we can then say that there's 2 amps going through here. And remember, P equals IV, so we found the I. We just have to find the V. So for the V, what we do is we look at this loop and we say, okay, we know that there's 15 volts between here. And now that we know there's 2 amps here, we know that there's 2 times 10 equals 20 volts here, because it's 2 amps going that way times the 10 ohms. So I'll write in red instead of keeping on using this laser pointer. So we have plus minus 20 volts there. We have plus minus 15 volts there. And we know that in any loop, the total voltage is going to like sum to 0. The other way you can think about that is if you were to like think of this as 0 volts, that's one of the symbols for 0 volts. That means from here to here it's 15. So then if we go up another 20, it'll be 35 here. So that means plus minus, this has to be 35 volts. That's kind of what he does here in more explicit math terms, but what I just said is how I personally would think about it. Basically, if we know that it drops down 20 volts here, and then it drops down another 15 volts here, then it has to go back up by 35 volts there. So now we have, okay, we have our voltage source. We know it's 35 volts, and we know that there are 2 amps going up through it. Remember what I said from last time? It's positive if the voltage drop is in the direction of current, and it's negative if the voltage rises in the direction of current. Here, we see the voltage is rising in the direction of current, so our power is negative 35 times 2, which is negative 70 watts. Okay. I'm gonna go through these just kind of as fast as I can. I'm not gonna go through this one as much because I want to get to the new stuff. So here, source transform, you take these two, you source transform them into this. Then you can take these two things in parallel and you get this. And then you source transform it back. So you source transform these two back so that you can get these two resistors in series. Basically, you can only combine resistors if they're very straightforward, directly in series or directly in parallel, with like nothing else between them. If there was like a source here, then you could not say these are in parallel because their ends, for things to be in parallel, their ends have to be directly connected to each other. If you had you had a voltage source here or you had a current source here, then you cannot say that those two things are in parallel. So basically, the goal of this kind of question is to um, make it so that the resistors are right next to each other. And you do that by kind of flip-flopping back and forth through your source transformations. So again, yeah. So again, let me go back to laser pointer. So you're here, you source transform to these two back into this, and then you can combine these two resistors. You combine those two resistors, yeah, those two get added together. And then finally, okay, you have, let's imagine this as like 0 volts. So if this is 0, then we have 10 volts here and we have 6.6 volts here. And then the current that he did here is just that 10 volts minus 6 volts, because if V equals IR, right, the V is going to be 10 minus 6.6 equals I times 18.33. We just solve for that I, and that's how we get here. And once you have the, uh, yeah, once we have this I, then we know the current going through the 10 volt source, and the voltage goes up in the direction of current, so we say it's negative. One other thing I should have mentioned at the beginning of this question is it says we're finding the power associated with the 10 volt source. So we're finding the power associated with this. If we want to find the power associated with this source, then we cannot do any source transformation to this source. Because if we mess with this source and we get an answer, then like that answer won't be correlated with this anymore. It'll be correlated with some source transform that you've done that no longer represents the original situation. So when you're doing a question and it asks to like, let's say it said find the power associated with this thing, with the 15 ohm resistor, then you can do whatever you want to the rest of the circuit, but you have to leave this alone. So that's why in this question, everything was done like on the left side and left the 10 volt source alone so that you can end up getting a current through the 10 volt source and it works. Okay, done with that. Now on to new stuff. Sorry I rushed through that, but I think it's useful, but I want to focus on the new stuff. Also, if you have questions at any point, feel free to ask in chat. I have it open on my screen and I can read it. Or just speak up. Okay. New stuff. We got node voltage method. Correct me if I'm wrong, but I think that's like the main new thing you've learned. You might have learned mesh current in class on like Wednesday, but that's for the next quiz. So node voltage method. The idea with node voltage method is the methods are kind of annoying because node voltage method uses Kirchhoff's current law, while mesh node voltage method uses the current law, while mesh voltage, or no, I can't speak. Mesh current uses the voltage law. But anyway, we're using KCL, which if you remember is current going in equals current going out. And we will see why this is useful in a second. So the core problem solving method of like everything you're going to learn in this class is write some equations that relate things to each other until you have enough equations to solve for all the variables you have. So let's see. Does he have a nice example I can look at in his notes? Or I'll pull one from your homework or something. I don't know. This is just a random example circuit I will draw. Actually, I should just start doing examples because I think that'll be the most useful thing. What's one that is easily doable? Uh, Sec. Guess I hopefully you all go to class. I would highly recommend going to class. I know this is somewhat of a novel concept to some people, but it is very useful. Little known fact. Uh, so I think basically the idea with node voltage method is you have some circuit. I'm just kind of making this up on the spot here. Um, let's say it had a third path. Here I don't know, we got some other voltage source. There's resistors. It's going crazy. We don't know what's going on. There's another resistor here. So what we do is we define voltage, or we define points where like a lot of components meet, right? Oh, I should put something here as well. We define points where three or more uh components meet. So like we define this as like V1, this as V2, and then where the most things meet, which is basically for every question in this class going to be like the bottom side of the circuit. We define that as 0 volts, which you can either write as this little symbol or this little symbol. I think those are the only really ones. I like this one. I just think it looks nicer. Um, so we define this as 0 volts. Let's say this has, I'm not actually gonna like draw out the things right now. We wouldn't define here because here only two components meet, and here only two components meet. And then what we do is we write the KCL equations for V1 and for V2. So basically we say, okay, there's a current here, there's a current here, and there's a current here, and there's a current here, and there's a current here. And all of these currents have to obey this law. And then when we do that, we end up getting enough equations that we can basically solve the whole circuit. And it's beautiful and it works. Um, and it's kind of hard to explain without just properly doing a example. So I'm going to do an example. I'm just going to get going. Use node voltage method. I'll start with one with just one node to make it as simple as possible. Um, and again, these are like questions from previous quizzes, so you'll probably get something kind of similar to this. Uh, Definitely not going to be the exact same questions. Orman updates them. Um, but you can expect a very similar level of difficulty from things on your quiz. So, okay. So this is the circuit, and it says find power of dependent voltage source. So find the power. That means we have to find this current and this voltage. So that's our goal. If you wanted to do this on a quiz, you could start by writing P equals IV, and you'd get like half a point for that. In what circumstances do we need one makeup voltage? So circuit, I will probably get to that question as I do examples. Okay, so what we want to do first for node voltage is define something as 0 volts. Basically, you can always just like see at the bottom here, there's everything meets. So I'm going to say everything along this bottom side is 0 volts. Very important thing to note. If it is connected by a wire, then this point and this point and this point are all 0 volts. What we're also going to say that also applies to the top. A lot of people make this mistake on quizzes, and don't be that person. This point and this point have the same voltage. You see, this is like V1, and since it's connected by a wire, this is also V1. Crazy. But you'd be surprised. A lot of people will write like V2 and then get very confused when they're writing their equations because there's no actual current flowing this way or that way because it's the same point, electrically speaking. So what we do is we say, okay, at V1, I usually do like V1, put a little colon, and then start writing my equations. So what's going to be the current? Okay, wait. Other aside, Zorman in class, I think, talked about how you're supposed to like kind of guess which way the currents go and give them signs based on that. I personally don't do that. I always just assume every current is going out because if you if it's not going out, then you'll just get a negative number and that's fine, right? If this current's actually going that way and we guess that it's going out, then for our final answer, we'll just get that like this thing is like negative 3 amps, and that means it's actually going in the other direction, but we don't really care at the moment. Um, the only exception to this rule is if there was like a current source up here and the current source is going in, you cannot change a current source. So you can't like pretend the current source is going that way. If something's going in, if you have a current source going in, then that's negative. I'll write this down somewhere.
Wouldn't you just be able to put like if the current source was like 2 amps, like just put -2 amps?
Yeah, it is. That's what I'm saying. So that's the only case where you will put a negative for this method. I'll current going in is negative, out is positive. What I'm saying is that in class, Zorman will like he'll like make a little educated guess about what direction he thinks the currents are going in. So like he might say this one's going this way, this one's going this way, this one's going that way. And then when he's writing his equation, he'll be like, okay, this current here, I'll start with the one on the left here. This would be like 9 volts minus V1 over 20 ohms. And then since it's going in, this will be negative. What I say to do instead is if you look at this, this is mathematically equivalent to V1 minus 9 over 20 ohms. You just take this in here, swap these two around. And it's just much easier to leave everything where you have the node you're looking at in the first place. But by Zorman's method, that would mean we are like guessing that this is going out. And then the one exception to this case is when you have a current, like this is 2 amps, then this, and it's going in, then you just have to say -2 amps. Another important thing, let me finish writing out this node voltage equation before I get too ahead of myself. This was not actually real, so I'll erase that. Okay, so back to the question. So our first current here is going to be our V1 minus whatever this point is. This point we actually just know is 9 volts because we have a 9-volt source here, and that's saying that there is a 9-volt difference between this point and this point. We know that this point is 0 volts, so therefore if we go up 9 volts, then this point has to be 9 volts. So that's just given. You don't have to think too hard about that. And then if we have V1 here and 9 volts here, and we have a resistance of 20 ohms between them, then V equals IR, then I equals V, or like the delta V over R. And that's how we get this little equation here. Then moving on, this is a similar thing. This is a dependent voltage source. You can tell because it has the little plus and minus in it. And again, we know there's 0 volts there, and then there's going to be VA over 2 volts there. We don't know what VA over 2 is yet, but that's okay. So again, we're going to say V1 minus VA over 2 over 10, and this should be a plus. So, because it's going out. And then finally, for the third one, this is, as I said earlier, here we have V1. This is electrically the exact same point. So this is also V1. So this current is the same as that current. So that's just going to be V1 minus 0 over 40. And those will all sum up to 0. It's basically saying all the sum of everything going in cancels everything going out, or like everything going out is 0. This is the simple case where we only have like one node that we care about. And then the other thing that we'll say is that because right now we have one equation with two unknowns, we want to get two equations, two unknowns. So this is where Zorman will do what is like the dependent source equation. And for that, we just kind of define what VA is. And VA in this case is going to be equal to V1 minus 9 volts. And that's like pretty straightforward because VA, or I guess it's actually the other way around. Sorry. Since you see VA in the question was defined as plus minus VA, then basically if we have 9 here and we have 0 here, then VA would be 9. If we have 9 here and we had 4 here, then VA would be 5 because it would be like, you know. So what we can say is that VA equals 9 minus V1. And that's how we get here. And now we have two equations and two unknowns, and we can just solve for it using whatever algebra you want. I'll do a quick example of how that might work, and I will try my best not to mess up. So start multiply by your biggest common or biggest denominator, or like biggest common factor, smallest common I don't remember the words. It's been a while. But yeah, we got 10 ohms, 40 ohms, so I'll multiply everything by 40. So we get 2v2. This will be minus 18 plus 4. Oh, I don't know why I wrote v2. There's only one voltage here. 2v2 minus 18, 4v1 minus this is going to be times 4, so it's times now it's just 2va, I believe. And then plus v1 equals 0. Please correct me if I'm doing anything wrong. We combine all our like terms. We got 2 plus 4 plus 1, 7v1 minus 2va equals 18. And then we actually know what va is from over here. So we put that in. 7v1 minus 2 times 9 minus v1 equals 18. 7v1 minus, and then that would be minus 2. So I'll actually just skip a little step here. 5 minus, I won't skip a step. 7v1 minus 18 minus 2v1 equals 18. Let me make sure I'm doing this right because it seems like I'm about to get v1 equals 0. And that's not right. Oh, no, it adds. Okay, yeah. So we get 5v1 equals 36, and then v1 equals 36 over 5, right? Is that 5? Oh, no, I messed something up. Hold up. This is minus here. We have a minus on the outside. So this is a positive, and then this is a okay. This is a 9, and then this is a 4 volts. And then remember, we're still not done with the question. However, now we have much more information we can use to solve the circuit. Because we know that at this point, I'll write this in blue, here we have 4 volts. So if we have 4 volts there, then we know that VA is equal to 9 minus V1 from before. So 9 minus 4, which is 5 volts. So that means our dependent voltage source is going to be VA over 2, which is 2.5 volts. Wow. And then last but not least, remember power equals the current times the voltage. So we also have to find the current. So the current here is going to be, if we remember back here, okay, we were looking at the current going out. When we were looking at the currents in general, it's the voltage at one point minus the voltage at the second point divided by the resistance. Because current will like flow between the voltages depending on what the resistance is. So I will equal V1 minus VA over 2 over that 10 ohm. And we have all of these now. So V1 is 4 minus 2.5 over 10. And that's 4 minus, yep, that's 0.15 amps. Yeah, that sounds right. Yeah, because it's 1.5 over 10. And then we say power equals current times voltage. And before we do this, let's look at if this is going to be positive or negative. So if we found VA is 2.5. So we have 2.5 volts here and 4 volts up here. Current flows from high to low, so it's going down. Here we have a 2.5 volt drop and it's going down. Remember, if current falls in the direction, if voltage falls in the direction of current, then it's positive. And here we have that situation. So this is going to be a positive power. So the power is going to be 2.5 times 0.15, which is 0.375 watts. And that would be your final answer. So again, I said a lot of words. How did I get VA equals not okay, let me finish this up. I said a lot of words, but the gist is you write your node voltage equation, you write your little dependent source equation. Basically, you write enough equations until you have an equal number of unknowns as you have equations. You have two equations, two unknowns, three equations, three unknowns, etc. Um, and then you solve the equations and you get your answer. Um, okay, to address the questions here. How did I get the current directions for V1? As I was saying earlier, I personally like to assume that all currents are going out. It doesn't matter what direction you guess because the math will always work out the same, but it is significantly easier if you just always assume the currents are going out. Yeah. The exception, again, as I said, I think I'll do an example, or I'll make sure I do an example where, yeah. The next example I'll do is a better example of writing the equations. But basically, I just always assume everything is going out. And then how did I get the VA equals 9 minus V1? So VA, I'm sorry, it's kind of messy here. I'll write in red on top of it. So um, can I get this a bit cleaner? Hold up. There's a bit too much going on here. Um, oh, and by the way, I think it is points on your quiz to like draw the little arrows around each node to say what direction you're guessing the current is going. So make sure you draw those little arrows. Okay, so how did I get 9 minus V1 equals VA? So VA in the question was defined as the voltage across this resistor. The voltage across this resistor is the difference between the voltage at these 2 points. This point we have defined as V1. That is the variable that we have made up and are using to solve the circuit. And we have also defined this bottom section as 0 volts. So then the difference between this point and this point is going to be, as I said earlier, this section here. This voltage source means that there's a difference of 9 volts between the bottom and the top of it, between the minus side and the plus side of it. So if there's 0 volts on the bottom here, then there has to be 9 volts on the top up here. And then again, VA is the voltage across this resistor. So that means that VA is 9 minus V1 because we have the plus side over here and the minus side over there. You know, if this was like 4 volts, then it would be, if there's 9 volts over here and there's 4 volts over here, then there'd be like 5, VA would equal 5. Okay, how did I get the V1 minus VA over 2 over 10 for current? So that's the same thing that we did when we were writing the node voltage equations. So you're asking about this. So if you look, this is the same thing as what I did here, which is the same thing as this current coming out of this node, right? We have V1 here, and here, as I said just now, we have a voltage source where at the bottom we have 0, and at the top we have 0 plus VA over 2, which is just VA over 2. So we have, here we have VA over 2, which we have found to be 2.5. So we have 4 on top, we have 2.5 on the bottom, or we have V1 on top, we have VA over 2 on the bottom, and they are separated by a 10 ohm resistor. Current will flow from high to low based on the resistance by the equation V equals IR, or I equals V over R. Here, the voltage difference across this resistor is going to be the voltage at the top minus the voltage, basically the high voltage minus the low voltage. So that's why we say the V1 minus the VA over 2, because this is the voltage across that 10 ohm resistor. So we get the voltage here, which is 4 minus 2.5 is 1.5, and then over 10 is 0.15. So we know that we have down here, we have 0.15 amps going down. So if you want to find the power at the 9 volt source, the current would be I equals, yes, exactly. Okay, yeah. So if we wanted to find the current here, so even though we kind of guessed it was going that way, we found that, okay, actually there's 9 volts here and there's 4 volts here. So the current's going to be flowing that way, which means that if we want to find the voltage to the 9 volt source, we would be looking at this current through the resistor. And yeah, just like you said in the chat, it would be 9 volts minus 4 volts over 20. And that would be the current going through the resistor, which is the same as the current going through the 9-volt source. And you could use that to find the power of the 9-volt source as well. Okay, I'm going to go over onto the next kind of question you'll have on the quiz. So yeah, the quiz, if you have like one node or two really simple nodes, then you'll probably have to solve for something specific. But something you'll see a lot in this class is they'll give you a complex circuit and they'll say, okay, write every equation you would need to solve for some particular value. And in that case, you just have to write the equations. You don't have to solve anything. It's quite nice. They're much easier to grade than the other kind of questions. And also they're hopefully easier for you guys as well. So this circuit is going to look kind of scary, and it will take me a good like couple minutes to draw, or it'll take me like a minute to draw it, and it'll look really bad. But here we go. This is like similar to one of the like bad circuits you would get on your homework and then hopefully plug into an equation solver. Yeah, by the way, if you're on the homeworks, if you get like a bunch of equations, like you're allowed to use an equation solver. Just make sure you plug it into the equation solver correctly. Um, just for your own sake. I don't know. I think that's everything. And now, okay, 12 volts, 3 amps, 5 ohms, 4 ohms, 8 ohms, 2 ohms, 7 ohms, 3 ohms, 5 amps. And then this part down here, I guess that wouldn't be labeled for you. So this would be the circuit you're given, and then they say, write all equations to find, let's say, in this specific example, it says everything you need to solve the circuit, but oftentimes they'll say like everything you need to find the current through the 5 ohm, that's a 5 ohm resistor. So when they give you a question like this, it's kind of like you just do the node voltage, and then you're also going to have one more equation for like finding this current. So in this case, again, what we want to do first is define something as 0 volts, which in this class, I cannot think of a time when it has not been just like the bottom section. So here, this is 0 volts, this is 0 volts, this is 0 volts, this is 0 volts. They're all connected by wires. It's all 0 volts. And then we define the kind of, I think, what does he call them? The important nodes, I don't remember. But it's the ones that you define as variables are the ones where more than two elements meet. So here there's only two things meeting, so we don't care about that point. But uh here there's one, two, three, four things meeting. Here there's one, two, three things meeting, and here there's one, two, three, four things meeting. So we're going to define those three as nodes. So this can be our V1, this can be our V2, and this can be our V3. You make sure, again, but don't get tricked by like how they draw it. Does it matter which node you define at the bottom? No, it does not matter which you define at the bottom as ground because all of these are the same node. Even though it's drawn like there's a different node here and here and here, since they're all connected by a wire, like you could, if you wanted to, you could draw the circuit like they all meet at one point and then go back up, and this could be one node, and that would be the exact same circuit. Can you expect to see supernode on this quiz? I do not think so. Yeah, but you see how like this is the exact same electrically speaking as this. That's a very important concept. Make sure you keep that in mind. But yeah, you could have like drawn it here. Yeah. And also, if you do for some reason choose to like decide ground is up here, you will end up getting the same answer. It'll just be a lot more annoying. Um, can you do a source transform? Again, like you can, but for this question, it's you don't actually have to solve anything. Like it's just write equations. So there's not really any point in messing with the circuit. You'll see this in a second. So basically, all you need to do is just write the node voltage equations because that'll be enough information to solve the circuit. So for V1, again, if you remember what I do, I like to say, okay, and then remember, this is V1, and then this is also V1. These are the same point. You could think of it as these things all meeting together right here, and this would be the same circuit. It's just they chose to draw it like this. But that means we have to be looking at the current here, 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 and here. And again, I will assume that everything I can pick goes out. But then here we cannot say this is going up because this is a current source and this is defined as like going into the node. So for V1, what do we do? Okay, we have to write the equations that we've written before. So here, just like before, if this is 0 volts, we go up 12 volts. This is now 12 volts. So this first one, it's going to be V1 minus 12 over 8. If you want to use your units nicely, you can. So V1 minus 12 over 8. This is going to, remember, since we're guessing that everything, or we're saying that every voltage or every current is going out, then this is positive, and then we're going to do the next one. I'll do the one going to through the 4 amp. So this would be V1 minus V2 over 4. And then the next one, now I'm going to do this one here. This will be V1 minus V3 over 5. And then this is, because this is also V3 for the same reason I just said for the ones above. And then for the 3 amp, since the 3 amp is defined as going into the node, we have to do minus 3 amps. And that all equals 0. Remember to write the equals 0, because otherwise it's not actually an equation. Oh. Okay, so that's equation 1. For V2, we do the exact same thing. I'll start with going left. V2 minus V1 over 2. And I know you might be thinking, oh, but we just guessed it's going that way. Why are we guessing it's going that way? Like, it really doesn't matter. If we guessed it was going that way, like the equation would be V1 minus V2 over, oh, this is supposed to be a 4. Whoops. If we guessed it was going the other way, you'd get like this thing, but then again, you factor the minus in and you end up just getting this anyway. So just always just guess they're going out. It makes your life easier. So we have V2 minus V1 over 4 plus V2 minus 0, the one going down, over 2, and V2 minus V3 over 7. And that all equals 0. And that's it. You have 3 paths for current, 3 terms in your equation. And another thing, always, you always want to make sure that the units of these terms will turn into currents. Because like I equals V over R, this is a voltage over resistance, voltage over resistance, voltage over resistance. In this case, this is a current already, so it's fine. But that's like a quick sanity check you can do for yourself to like make sure you've written your terms right. You never want to do I've seen people get very confused and be like maybe someone, I've definitely seen this before where like someone will see this up here and be like, oh, there's a thing between 2 voltage sources. It must be V1 minus V3 over 3 amps. And that just doesn't make any sense because these terms are all supposed to be currents. Because remember, this is all coming from, the current in equals current out. And this is not a current. So yeah. So don't get tripped up by that. It's always each term should always evaluate to a current in terms of the units. It should turn into amps. Yeah. So then last but not least, we have V3, which has a similar thing where we have V3. I'll start, and V3, like V1, we have to consider many here, actually. I'll do these in blue so you can see what I'm doing. We have one here, we have one here. This one is going in, and then we have one here, and we have one there. So there's going to be 5 terms for the V3 equation. Don't get too scared. It's still the exact same process you've done before. So I'll start with the 7 ohm. So V3 minus V2 over 7 ohms. And then going down, we have V3 minus 0 volts over, I think that's supposed to be a 3 ohms. And then coming in from the right, we have a current going into the node. So minus 5 amps, that's supposed to be amps. I miswrote that. Minus 5 amps, and then plus V3. If we're looking at the this 5 ohm resistor here, it's going to be V3 minus V1 over 5 ohms. And then last but not least, for this 3 amp source, that for equation 1 was a, oh, I didn't fix this again. Let me turn that back to what it was supposed to be. For equation 1, since this was going in, we said that this was a negative 3 amps. Since it was going into V1, it was negative. Since it's coming out of V3, it'll be positive. So this is going to be a plus 3 amps. And that all equals 0. Okay. And then last but not least, for this question, it says write all the equations to find the current through the 5 ohm resistor. So these equations here are technically enough, but if we also want to find the current through the 5 ohm resistor, we can, or we have to explicitly say that like the current of the 5 ohm resistor, which is here, is going to be, okay, it's going to be V3 minus V1 over 5, which is what we had, which we've written before. So V3 minus V1 over 5 ohms. And then this alone, so just these things, you write those and then you're done with the question. You've written it all. Someone asked, how can there be currents flowing in opposite directions through the 4 ohm resistor? Again, as I said earlier, it's like there's not actually currents flowing through opposite directions. We just say there are for the sake of the math. What you're going to get is that like what it is so like for this 4 ohm resistor, it's these two equations. And if you look at these two equations, this one, like this one, they're negatives of each other. Like you just have these two things flipped. So for one equation, like you'll get, I don't know, let's say we end up finding that this is, I don't know, like 4 volts and this is 2 volts, right? In one direction, for this equation, you'll get 4 minus 2 over 4. You'll get like 1/2 amp. And then for this equation, you'll get 2 minus 4 over 4, and you'll get negative 1/2 amp. So if we say that there's like a half amp flowing this way and a negative half amp flowing that way, then it's actually just saying the same thing. Because a negative half amp just means we actually have a half amp flowing in the other direction. Hopefully that makes sense. But the idea is that like the math always works out. You can guess whatever direction you want. I highly recommend always guessing that everything is flowing out of every node, because then all of your signs are positive, and you always have the like the V3 in the first slot, or the V2 in the first slot, or the V1 in the first slot. Um, Again, with the source transformation that you're asking about, like you can do the source transformation, but there's no reason to. Like it's yeah. There's not really a point to doing the source transformation because you're just writing equations. Like you don't have to solve anything. Like this is enough. You've done the whole question at this point. There's not really a reason to. But it would be correct. It would be kind of odd though. Um I guess there's one other case. So I'm just gonna kind of make up an example here for something that you'll see. If we have some circuit where we have like some stuff, I'm just gonna draw two nodes. Because what I want to focus on here is what happens if you have some stuff like this, where we have V1 and V2 here. If you get this and you're writing an equation, let's say this is 3 volts, this is 10 ohms, and we want to write the equation going that way and that way, what you have to do is you still have to look at what the current through this resistor is going to be. So let's say we're writing for V1, right? For the V1 equation, we want to look at what this current going to the right would be. And again, what you have to do is remember, okay, for a resistor, V equals IR, I equals basically the voltage on one side minus the voltage on the other side over the number. So it's going to be the voltage here minus the voltage here divided by 10. So the voltage on the right side here is just going to be V2, but the voltage on the left side here is going to actually be V1 plus 3 volts. So what we have here is I'm like kind of just making up a situation here. Um, but if you were writing an equation and you were writing like the term going to the right, then you would write V1 plus 3 minus V2 over 10. And if you were doing it dot 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 plus dot dot dot, you know, um, and if you're doing it for V2, you would say, okay, V2 minus V1 plus 3 over 10 plus dot 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 plus, yeah, yeah. That's just a random point I wanted to bring up because some people get confused there. And can I explain the last part? So the question was write all equations necessary to find the current through the 5 ohm resistor. This last equation is just the current through the 5 ohm resistor. Again, the current through a resistor is the voltage across the resistor divided by the resistance. The voltage across this resistor is like V3 minus V2 or V3 minus V1. I guess if you got this question, it would probably be like it would give you an arrow and it would be like this is IX and it said find IX. And so IX in this case would be V3 minus V1 over 5. Just because that's the definition. Could I re-explain the dependent source equation for the first problem? Sure. So for the first problem, this me. Is there another question I can do that'll have a dependent source equation that'll just make a bit more sense? Yeah. I'll do okay. I have like just go a bit over time, it's fine. Um I'll do yeah, I'll do this one and I'm just gonna go through this fast. This one has one dependent source equation, but this one also has some other stuff. This one has dependent current sources this time. Okay, so our goal is to find the voltage drop across the 20 ohm resistor. And to do that, we're using the node voltage method. So again, first step, define our 0 volts. This is our 0 volts here. That means this whole bottom line is all 0 volts because it's all connected directly to each other by wires. And then we define our nodes as the points where multiple components meet, not just two. So that's going to be here, here, and here. This is V1, this is V2, this is V3. And then I'm just going to start writing equations. So for V1, it'll be, okay, we're going to guess out here, because there's resistors, but then we know that this current source is going in, so that one has to be negative. So it'll be minus 5I0. And again, we know this is a current source because it has an arrow on it. If it has an arrow, it's a current source. If it has a plus minus, it's a voltage source. Don't get that wrong. So we have minus 5I0 plus V1 minus 0 over 20. That's the current going down. Plus V1 minus V2 over 5. That's the current going to the right. And that will all equal 0. First equation down. Okay, next equation. We got V2 minus V1 over 5. That's going to be the current going to the right or to the left. And then we can either say, there's two ways you could go about this. You could either just say like plus I0, or you can say uh, V2 minus 0 over 40. I'll just leave it like that for now to keep consistent, but both of them will end up working out because I'll do the dependent source equation on the side real quick, right? The dependent source equation is just going to be defining what I0 is. Because if we, okay, yeah, I'll do it like, I'll say plus I0, because we've defined I0 as going down out of the node. Things coming out of a node are positive. And then plus V2 minus V3 over 10 equals 0. And then now that I've said this I0 once, I'll talk about how we deal with that, right? We just define what I0 will be. I0 will be the current going through this, so it's just going to be V2 minus 0 over 40. Or just V2 over 40, you know? And then last but not least, we have our V3 equation, which is going to be starting with the current going to the left, we will say V3 minus V2 over 10 plus V3 minus, and then here, as we can see, this is a dependent voltage source. So we have to look at, for the current going down, we have to look at what the voltage drop across the resistor is. For this resistor, at the top it's V3, and at the bottom it's going to be, okay, we have 0 here, and then if we go up 11 I out, or I naught, and then at this point we have 11 I naught. So what it'll be for our term here, sorry, it'll be, okay, plus V2, or, oh, this is, I'm in the wrong place, sorry. V3 minus 11 I naught, because that is the voltage at this point. And that is going to be over 5 ohms. And then plus, last but not least, we have V3. And then this point, hopefully you can all see by now, is just going to be 96 volts. So it'll be plus V3 minus 96 over 4 equals 0. And then, as I said before, the dependent source equation is just defining what that thing that the dependent source equation is just defining the variable that is used in dependent sources. So here, the dependent sources use I naught in the equation. And so we say, okay, this is I naught. And now we have 4 equations and 4 unknowns. We have V1, V2, V3, and I naught, and we have 4 equations. So this could hypothetically be solved. However, don't forget, this question said, what is the voltage drop across the 20 ohm resistor? So the last equation we'd write is the voltage of the 20 ohm resistor is equal to, okay, the 20 ohm resistor, on one side we have V1, and on the other side we have 0. So the voltage drop across that is going to be V1 minus 0, which is just V1. And once you have that, that's all the questions, that's all the equations, and you have your answer. Okay, I got 5 minutes. I will do one more question because there's something I want to get to here that if I don't get to, I am sure I will see many people mess it up on the quiz. Okay, so okay, so this question, it says use node voltage to find the power of the 7 ohm source, or the 7 ohm resistor. So find this. So that means you actually have to solve the whole question. You might look at this and say, oh no, that looks complicated. But the thing about this question is there's actually only one node because all of these are connected together. So if we were to go about this in the normal way, right, we say, okay, it's on the bottom. We're going to say this is 0 volts. And then we look at where we put our other nodes. So again, a node is where more than two components, or the Important nodes are where more than two components meet. And we only really have one place where that is. We have here and here and here. Those all look like different nodes, but again, since they're all connected by a wire, we basically just have one node, V1. That's V1, that's V1, that's V1. Again, I'll do that little, you can think of this as everything meeting at one point here, right? You just have one node. They just draw it like this. And what I'll see on quizzes is people will try to say like V1, V2, and V3, and then they'll be writing their equations and they'll be like, oh no, what's here? We have V1 minus V2 over 0 ohms. What? And it just doesn't work. Don't be that guy. Yeah. So again, we only have one node. We just have V1. Everything is V1. I will simply write V1 once, and we will write our one equation. So we got V1. And the V1 equation is going to be, I'll draw these little arrows in blue. Okay, we got one there. I'll say one there. That one has to go in because it's a current source. We have one there, and we have one there. So I'll just go from left to right. So we got V1 minus, and then again, you look at the point here, you look at the point here. At the point on top, it's V1. At the point on the bottom, it's 0 plus 120, which is 120. So it's V1 minus 120 over 20 plus at this point is 0. And then at this point, it's V1 plus 60 because the direction of this voltage source has the minus on top and the plus on the bottom. So from here to here, it'll be plus 60. So for this resistor in particular, if we're saying that the current's going down, it'll be V1 plus 60 minus 0 over 5. And then we have that minus 36 amps going in. And then we have plus V1 minus 0 over 4. And then going out to the right, we have two resistors in series, which we can just add together. So it'll be V1 minus 0, because down here is 0. And then over that 3 plus 7. And that all equals 0. Then you do a lot of math. I'm not going to do it here. Uh, hopefully, hopefully you can all do math. Um, by the way, if you ever want to like check your answer and if so like the answer here, right, you're gonna solve the equation. You only have one unknown, you have one equation. It's just V1. You solve this, you get V1 equals 50 volts. If you want to check it, just plug it back into this equation. You should add everything up and it should get 0. So that's just, if you have a bit of time left on your quiz, you can do that as a sanity check. And if you did it right, if you wrote your equation right and you solved it right, basically, if you didn't mess up your math, you'll get that the equation checks out. That doesn't guarantee that you wrote your equation correctly, but it'll guarantee that you did your math correctly. Okay, but then we want to find the power through the 7 ohm. So that means we have to find the voltage drop and we have to find the current. So the voltage drop across this is going to be, or let's find the current first, because the current's easier. We know that here we have V1 because it's V1, V1, everything's V1, because they're all connected by a wire with no resistor. So the current through here is simply going to be, let's say, I of 7 ohm. The current through the 7 ohm is the same as the current through the 3 ohm. And that's the same as like the current if both of these were combined into one resistor. So the current is going to be that V1 minus 0 over 7 plus 3, which is the term we said here, right? Because that's what we were doing when we were finding this arrow that I'm drawing again. And V1, as we found, is 50, so it'll be 50 over 10, which is 5 amps. And then you can either plug this into like, I think, so if you have P equals IV, and you know that V equals IR, you can plug this back in and you get P equals I squared R. And that's an easy way you can find uh, that's the easy way you can find the power. Or you can think of it like, okay, I have 5 amps here. The voltage is 5 times 7, which is 35. And then you multiply these two together and you get power equals 35 times 5, which is 175. You'll get the same thing if you do, 5 squared times 7, which is 25 times 7, which is 175. And watts. Make sure you would say watts. Okay. How many questions should we expect to see on the quiz tomorrow? Um, on the quiz tomorrow, every quiz is 2 questions. For every quiz. Every quiz is 2 questions. You only have 2 questions. Supernodes will not be on this quiz, I believe, unless he like changes it. The past couple semesters, it has just been this quiz has just been node voltage. Next week will be mesh current. And then maybe the one after that will have supernodes or super meshes. But yeah, this one should just be node voltage. Um, and then again, why are we adding the 60 to V1? So here, the reason we're adding the 60 to V1 here is because if you look at this, this voltage source is kind of upside down. We're used to seeing them with the plus on top and the minus on the bottom. Here, the minus is on top and the plus is on the bottom. And again, a voltage source means that like from the minus side to the plus side, that's from the minus side to the plus side. If I have, Vx here, and this is 3 volts, then over here I have Vx plus 3. You can also think of this as on this side, if I have Vx, then over here I have Vx minus 3. It's just like you can think of it as like there's like a barrier between the two. And on one side you have this, on one side you have this, and it's separated by that 3 volts. Here we have V1 here, and this is a 60 volt source. So if we go from the minus side to the positive side, it has to go up 60 volts. That's that. Um, there will not be supernodes on this quiz. I'm like 90% sure, 95% sure there will not be supernodes on this quiz. Yeah. I think like there's never been. Supernodes might be on like I don't even know what that would be on, but it wouldn't be on this one. Yeah. Are there any other questions? Will it be on the everything's on the final exam? Yeah. There's only one exam in this class, and it's the one at the end. And you can just assume everything is on that. The final exam is like 10, 10 quiz questions stapled together. So don't forget stuff. Hee hee. Okay. With that, I will end the recording.